Homework solution 4.3, a 2000 kVA, 11 kilovolt, three-phase Y-connected generator has a resistance of 0.3 ohms and a reactance of 5 ohms per phase. It delivers full load current at 0.8 lagging power factor and rated voltage. Compute the terminal voltage for the same excitation and load current of unity and 0.8 power factor leading. So in example 2, what we did is we calculated what value of EF we needed to change the system to get a constant terminal voltage. And in this, so we changed this to maintain this constant under different loads. And in this problem, what we're going to do is we're going to say, okay, well, if EF is fixed, what will VT change to under different loads? So that gives you some perspective as to what the difference between these two problems is. Anyway, the givens here are that we've got a power. Remember, powers again are in three-phase. This is kVA, so we know that's an apparent power. So S three-phase, its magnitude is equal to 2000 kVA. Guess you could have written that as 2 megavolt amps. We've got a voltage, 11 kV, so that's the terminal voltage. But remember, that's specified as line to line, so that's 11 kV divided by root 3. We were told what the resistance is. We know that the symbol for armature resistance is Ra. And then we've got the reactance, so that's X sub S. It's a big one, 5 ohms is pretty large. So that's what we were given. We were asked to find VT at IA rated, power factor equals 1, and IA rated, power factor equals 0.8 leading. So the solution to this, again, is we're going to start with the circuit model. And we've got the generator model here. It's got a load connected to it. It's got an armature current flowing through it. It's got a terminal voltage VT. This is RA. This is XS. And this is EF. I guess we could be more specific. This is EF at angle delta. And this is VT at angle 0 degrees. So the question is if we set EF to a certain value to provide the load with VT at 0.8 lagging and rated current, what happens if the load changes? So to do that, the first thing we have to figure out is, well, what does EF need to be to provide rated voltage and rated current to the load? So we can calculate IA. I'll say the magnitude of IA is going to be the magnitude of single phase power divided by the terminal voltage. I don't have to use a complex conjugate if I'm just doing magnitudes. And so IA is going to be 2000 kVA. I need to put that on a per phase basis, so I divide by 3. And then I need to figure out what that terminal voltage was. It was 11 kilovolts. But I need that on a phase quantity. So the magnitude of IA when it's the rated current is 104.973 amps. So anytime it says rated current, that's what it means. It's 104.973 amps, and we got that from rated power and rated voltage. So this generator was configured to deliver a lagging load, so an inductive load at 0.8 power factor. So if we drew the phasor diagram where IA lags VT, remember it looks like this. That's your terminal voltage. Here's your lagging current at a whatever phi is for power factor of 0.8. We can calculate that real fast. Power factor equals 0.8 equals cosine of phi. Says that phi is equal to inverse cosine of 0.8. And that's going to give me 36.87 degrees. That's that value right there. There's voltage drop across this resistor. Points that way. Voltage drop across that inductor. It's 90 degrees. degrees out of phase, and that's EF. Hopefully that's looking very familiar at this point. So this is VXS, this is VRA. So that's what the diagram looks like, and what we're trying to figure out in this point is EF, because it's our kind of our configuration value. So we can determine that EF in this situation using Kirchhoff's voltage law is going to be VT plus the current here. It's lagging. It's a rated current lagging. And then we want to know what this component and this component are, which was just 0.3 plus J5. So current times impedance gives those voltages right there. And so we get a value, the initial value of EF is 6,702.97 at an angle at 3.43 degrees volts. So if I set EF to 6,702.97 volts, if the load's drawing rated current at a 0.8 power factor lagging, I'll get a terminal voltage of 11 e to the third over root 3 at angle 0. So that's basically I've now calculated the initial conditions for the generator. And so what we want to do is calculate what happens. I believe in part A it says, well, what happens if the power factor of the load, the magnitude of the current stays the same, but the power factor of the load goes to unity. So in part A, what's going to happen is IA is going to be equal to 104.973 at an angle of 0 degrees. So I'm going to real quickly draw the phasor diagram for that to illustrate this problem. We've got the terminal voltage VT. This is in phase, which means the current or the voltage drop across the resistor VRA is in phase with the voltage because it's in phase with IA. Should have drawn IA first, sorry. VT and IA are in phase, therefore VRA is also in phase. VXS is 90 degrees out of phase with that. So the power factor angle is 0, but the power angle delta is not 0. We've got some non-zero power angle there. So previously, in the previous example, what we did to calculate this was EF is equal to VT plus VRA plus VXS. That formula is still true, but the problem is we now have two unknowns. When the load power factor angle changes, the magnitude of VT is going to change, so the length of this vector changes, and delta also changes. So if I were to write this all the way out, it's magnitude of EF at angle delta plus VT, is equal to VT at angle 0 plus VRA plus VXS. And we don't know this number, and we don't know this number, and we only have one equation. And laws of algebra are that you have to have as many equations as you have unknowns. So unfortunately, in this situation, we can't solve this using that problem. What we can do, though, is if we look at this, we see that this is a right triangle, and so we can use some laws of geometry to solve this problem instead. We could say that the magnitude of EF squared is equal to the magnitude of VT plus the magnitude of VRA squared plus the magnitude of VXS squared. So we're seeing this as a right triangle. The hypotenuse squared is equal to the base squared plus the height squared. So now we can solve this if we know the different magnitudes. And we do because we know the current and we know RA and XS. So Remember, if the load changes without any sort of adjustment by an operator, magnitude of EF can't change. So that is 6702.97 squared is going to be equal to VT plus VRA, just comes from the current here, times RA. So that's 104.973 times 0.3. So add those together, you get the base, so square that addition. And then we need this height right here, which is going to be 104.973 times the synchronous impedance, which was, synchronous reactance, which was 5. Square that whole term. So now you can see from geometry, we only have one unknown, VT. And we don't have to solve for an angle for VT because we know it's on the x-axis. So if we solve that, we get VT is equal to 6,650.84 at an angle of 0 degrees volts. So we get our terminal voltage that way. In part B, we were asked to solve the same thing, except now IA is going to be equal to 104.973, and I forgot the angle here, excuse me. It's 0.8 leading, so that's just going to be 36.87 degrees. So if I draw that phasor diagram, I've got VT as my reference. I've got IA as 36.87 degrees. That's phi right there. Got the voltage drop across that resistor, VRA, VXS, and then finally EF right there. So this one's a little harder to do because there's no obvious right triangle. And so what you have to do is you have to look at these diagrams and figure out where you can create a right triangle. There's actually a couple geometric methods on here. And the one that I'm going to use to create a right triangle is I'm going to use a right triangle with EF as the hypotenuse. So this right triangle here. And so the hypotenuse is still EF squared. Now I need to calculate the base. So the base is VT plus the projection of VRA in this direction here. So the projection of VRA onto the x-axis plus the projection of VXS onto the x-axis, right? If I just add VT plus the real part of VRA plus the real part of VXS, I get this phasor right here. So that is going to be VT plus the real part of VRA plus the real part of VXS. So that gives me this vector right here, which is the base of my right triangle. So square that. And then I need to know the height of this right triangle. It's going to be the imaginary part of VRA plus the imaginary part of VXS, right? The projection of VRA onto the y-axis and the projection of VXS onto the y-axis. So that's going to be the imaginary part of VRA plus the imaginary part of VXS squared. So symbolically, it looks pretty messy. It's really not too difficult to calculate though. We've got our value for EF right here, 672.97. 6,702.97 squared is going to equal VT plus, I need to know the real part of this vector, so I'm just going to go ahead and calculate these vectors here. VRA is going to be equal to IA RA, and that is going to be equal to 104.973 at an angle of 36.87 degrees times RA, which was 0.3. And so that gives me a vector right here of 31.492 volts at an angle of 36.87 degrees. Then I want to know this vector here, which is VXS is equal to IA JXS. So that's 104.973 at an angle of 36.87 times J5. That gives me a voltage of 524.87 volts at an angle of 126.87 degrees. So the real part of this guy is just 31.492 cosine of 36.87. And the real part of this guy here is 524.87 cosine of 126.87. Square all that. And then I've run out of room, so I'm going to just drop a line here. And then the imaginary part of this guy is 31.492 sine of 36.87 degrees plus 524.87 sine of 126.87, and then square that. Lots of numbers, but pretty easy calculation. Solve for the terminal voltage. You get 6,978.32 volts for the terminal voltage under that lagging load condition. Leading load condition, that's for a leading power factor.